Okay, good morning everyone. Thanks for coming. I hope you all had your coffee, so we're all awake this morning. I know I'm a bit tired from last night, but let's get into it. So my name's Daniel Chambers, and I work as a senior consultant for Redify. My Twitter handle's up on the slide, so if you have any questions or feedback, please feel free to tweet it at me, or if you see me around the conference, please do come up and have a chat. Happy to talk. So out of all the talks that I've done so far, my most popular one is probably the one where I introduce F# to .NET programmers. I like F#, and I think more people in the .NET space should use it to write clean and composable code. So you might then be wondering what I'm doing a functional programming talk in C# and JavaScript instead of in F#. Well, there's kind of two reasons. One is that I do have a talk later this afternoon on Haskell, so that's fulfilling my hardcore functional side. But the other is that what I realized when I did that F# talk was that whilst a lot of people like the look of F#, they can't just jump ship off what they're coding in right now. And for most people, what that means is it's probably C# and JavaScript. We've got years of investment in these code bases, and we can't just chuck all of that away overnight. I'm going to quote directly out of the Lord of the Rings and say what Boromir says is that one does not simply shift to F#. Some people are scared off by functional programming because it can be quite different from the typical imperative style code that most people write in their day jobs. But what most people don't realize is that they've been doing little bits of functional programming for a while now, because functional programming constructs have been stealthily added to C# and JavaScript for quite a few years. The problem is that most people don't use these features to their fullest extent that they could, and when I look at the code that I see written, there's a lot more that people could do there. So the aim of the talk is to show you how you can use these functional features of your language together with functional libraries so that you can get some of those functional programming benefits now in your day job. Then once you're used to this first level of functional programming, you'll be naturally attracted to more full-blown functional languages like F# and functional techniques. So first, a little bit of history to put functional programming in its context. So in the beginning, there was unstructured programming, where we used go-to statements to allow the programmer to control that flow of development, that flow of the program. So this allowed us to write programs that quickly grew out of control and ended up being quite messy. This is where structured programming was introduced to kill off that go-to. We lifted that level of abstraction up a notch by formalizing those looping constructs into for and while loops. We introduced procedures and subroutines, and they were added to split code out and make it more easy to reuse. Structured programming was an attempt to make the flow of control clear. This was a big step up from unstructured programming because it made that code much more easy to reason about because of those common control structures. Unfortunately, structured programming still has a nasty flaw, and that's global variables. Everyone here, I'm sure, knows the pain of global variables and how code that uses them is extraordinarily hard to understand and reason about. To solve this, object-oriented programming was created to kill off that global variable by providing language features that make it easy to encapsulate state. It does this by tying data and subroutines together into the concept of a class. It also takes further steps towards code reuse by introducing inheritance and composition. Again, we've lifted that level of abstraction up a notch with the aim to improve our ability to understand code and reason about it. This again allowed the complexity of our software to jump up. But as you probably know, there's still issues with state management in OO. While variables are local to classes, they're still variable and they're shared by everything in the class and possibly externally. Functional programming takes this to the next level. Its aim is to remove state altogether. State is variables whose values can change. We can remove state through the judicious use of pure functions, which are functions that have no side effects and therefore always return the same output for the same input. This simplifies the code by removing moving parts, where the moving parts in your code are those variables. Functional programming lifts that level of abstraction even further by treating functions as values. which makes reusing code trivially easy. It also allows for the implementation of libraries that act as domain-specific languages, which make it easy for you to focus on writing your business logic rather than writing control logic. So an example of such a library is LINQ, and the domain of LINQ is the sequences of values. So you're probably wondering, well, don't I need a functional programming language in order to do functional programming? And the answer is no. Eric Meyer of the LINQ and Rx, reactive extensions fame, he defines functional programming as a style of programming where expressions are more important than statements. This is a key point in understanding practical functional programming. Expressions take input and deliver a result, and we combine those expressions together to express a wider program. Expressions don't have side effects, they return a value. This means statements are the antithesis of expressions and therefore of functional programming. They have an implicit side effect against the global state, and since we're trying to eliminate state altogether, we need to get rid of statements and focus on expressions. So functional programming languages make writing code solely in expressions easier by adding language features to help support this. And good news, some of those features have been brought into the languages we use every day, such as C# and JavaScript. So let's have a look at how we can use our day-to-day languages to start doing a little bit of functional programming. So C#3 introduced lambda expressions, and this makes functions as first-class values easy. This introduced a wave of functional programming libraries to be added to .NET. LINQ is the best-known library. LINQ is basically functional programming sneaked into the language by stealth. So guess what? If you've used a bit of LINQ, you've already done a little bit of functional programming. LINQ is really a set of higher-order functions, that is, functions that take other functions as parameters, and that lets us deal with sequences of values using only expressions and no statements. This means that we can eliminate side effects and variables from our code when we deal with sequences. And it also allows us to write simpler and more readable code. So LINQ is typical of functional programming. It raises the level of abstraction up when we're dealing with a domain. In this case, the domain is of sequences, and the library allows us to reuse code that has already been written to deal with sequences. This means that we can write business logic that states what we want rather than how to get what we want. This style of declarative programming is easy to do when you're programming functionally. All functional programming languages will have a library like LINQ in them. However, in order to sort of sneak functional programming into .NET without scaring people, Microsoft used different function names to what you'd typically see in the functional norms. So for example, in most functional programming languages, the select method is called map. Aggregate is called reduce or fold. Any is called exists. So hopefully you're starting to realize that functional programming isn't a totally weird beast that can seem terrifying. You're already using it a bit with libraries like LINQ. However, what I see when I look at most C# and JavaScript code is that people are dabbling a little in functional programming, but they could improve their code even more by fully embracing it. So let's start looking at some practical code examples of how you could write your code more functionally to get rid of state and make your code more readable and maintainable. This way you can start taking further steps down that functional programming path and do it in your day job. So let me switch out of the slides. And I've got some first initial examples in LinkPad. So what I've done here is I've basically written some code in C#, and I've written an imperative version of some code, and then I've transformed it into a functional version so that we can sort of contrast and compare what that means for us. So in this first example, it's a very simple little algorithm. We're basically taking a string, which would contain someone's name, and splitting it up into first names, middle name, and surname in a name class. So this is some pretty typical logic we might write in our business applications. So this is the code that we'd look to write if we were writing this imperatively. So we take that string in and we're returning the name class out. So the first thing we're going to do is we're going to take that name string and we're going to split it up on spaces so we can just get out the individual names. And we've also used this overload, which means that if there's any double spaces, we get rid of those empty strings. Then what we're going to do is we're going to create that new name class, and it's going to be in an uninitialized state at this point. Effectively, all those properties will be null. Then we're going to write some imperative conditional code where we're going to manually check the length of the array, and we're going to say, okay, if there's one or more names, then the first name, so the first thing in the array, so we're going to manually index into that, will be our first name, and we're going to side effect against first name in order to store that. If we've got two or more names, we're going to manually index to the end of the array, grab the last name, store it as the surname with a side effect. If we've got three or more names, that naturally means we must have at least one middle name. So what we're going to do then is loop through the middle names with a manual for loop and start from the second element and go up until the second last, and then append them together in a string builder. Now, the string builder is naturally going to end up with a trailing space, so we'll have to trim that off when we take the string out of the string builder and then side effect it into the middle name on the class. Then we'll return that instance from the method. So this is pretty typical imperative code that I'm sure we've all written at some point. The first thing you'll notice here is that what we're doing is we're literally instructing the program how to get what we want. What we'd rather do is declare what we want and work at a high level of abstraction to make this smaller and more readable. So let's have a look at a first version of the way we might do that. So in this first version, what we're going to do is, again, we're going to do our split. And then what we're going to do is we're going to create the name class instance, but this time we're going to do it using an object initializer expression. So straight away what we're doing is we're initializing a name class instance, but at no point in this code here have we ever got a name class instance that's half initialized. This expression, when it evaluates and completes, will return a valid name. So this object initializer allows us to set our properties. So here what we're going to do to get the first name is, instead of manually indexing into an array and having conditional logic, we're going to lift our level of abstraction up and think about sequences. So we have an array is a sequence. Our library for sequences is LINQ, and LINQ has a first to default method that we've probably all used at some point. So this is a great example of where we could write manual logic, but really, if we work at this high level of abstraction and declare what we want rather than how, we actually end up with code that's a lot simpler and much more readable. To get a surname, what we're going to do is we're going to use a ternary expression. So ternary expressions are great for allowing you to write conditional logic, but then stay writing expressions rather than writing statements. So here, if we've got one or more name, we're going to use the last. So again, instead of manually indexing into the end of an array, we'll just say, give me the last. So again, we're sort of working at that declarative space. For the middle name, we're going to use a ternary expression to check to see if we've got three or more names. And then if we do, we're going to write a bit of a LINQ pipeline here. So in C#, because C# isn't a full-blown functional programming language, we don't have nice ways of composing functions using operators. So in C#, we typically use this fluent style where it's generally implemented using extension methods where we can sort of dot from one function to the next. So in this case, what we're going to do is we're going to take our name sequence and we're going to skip away from the first one because that one's just our first name, and then we're going to take up until the last element, but not including the last element. Then what we're going to do with our sequence of middle names, because that's what that expression effectively represents now, is we're going to aggregate it down to a single item. So aggregate is how you would take a sequence of items and reduce it down to a single one, which is typically why it's called reduce in functional programming languages. So here, this will reduce it down to a single name, but of course, because of the way this works, a bit like our imperative version, we're going to end up with a preceding space in this case, because the very first time we're going to take the first middle name and add it to this empty string. So we're going to end up with a space. So trim solves that for us. So what we can see here is that we've written code that's a lot shorter than what was there before. It's much more declarative. We've eliminated all the state in that code and all of the side effects, and we've just worked with expressions rather than with statements. But there's still something here which is a bit icky, and that's that trim. Wouldn't it be nice if we could just get a string in the right format to begin with rather than getting one that's a little bit wrong and then fixing it? So let's look at how we could do that. So this is where we could kind of look around in our libraries, and we find out that, okay, we've got something called string join, and that will give us the behavior we want. It will take a sequence of strings and then give us them back joined together, in this case with a space. But if there is only one string, it will just return that string rather than trying to mash it together with the empty string. But we've now lost the readability of the code because, again, C# not being fully functional, we do have to use string join in this prefix position rather than where we'd prefer it being in sort of postfix position. But we can work around that quite easily. So what we can do is we can just create a little extension methods class and then create an extension method off of the IEnumerable of string and then just pass through to the string join. And what this means is that we can actually end up in the place where we want, where we can add string join to the end of this pipeline of functions, and now this reads much more nicely. So you can kind of see what we've done here is we've been able to reduce our code down, we've eliminated the use of statements and just work with expressions so that we can sort of lift our level of abstraction up and program declaratively, stating what we want rather than how to get what we want. So another example I've got for you here is this one. So what we've got here is a little data model. So we've got something called an application. So you can kind of think of an application in this case to be like what one would fill out on paper. So like, you know, you're filling out a form. And this form has a life cycle and it goes through a number of state changes. So on the model, we track the state changes this thing's gone through. So, you know, it started out in state 1 and we record the time that it moved into that state. And then at some point it moved into state 2 at this time, and then it moved into state 3 at this time. Now, imagine where we're taking this model and we want to display it to the user. You know, and one of the nice things we want to do for the user is not just show them the start date, but we also want to show them how long it was in a particular state for. So how we typically handle that is we'll create a view model for the state change, and on that we'll calculate that duration, and then just to make it easy to bind it into the UI. So what we're going to do is write a bit of code here to calculate that duration. So if we think about how we're going to do that, it's basically a set of subtractions. So in order to figure out the duration of a state, we basically want to take the time that it started and the time that it ended, and then subtract the start from the end to get the duration. So we can say that the end time of a particular state is the start time of its successor. So in this case, to get state 1's duration, we want to take state 2 start date and subtract state 1 start date away from it. And then state 3's, to get state 2's duration, we want to take state 3's start date and subtract from it state 2 start date. And for state 3, it's a little bit different because that's the state we're currently in, so there is no real end date. So we'll just use now time to represent the end date, because that way we can say, well, how long have we been in this state up until now? So if we were going to write some imperative code here in order to calculate this and create those view models, what we'll have is a function that probably looks a bit like this. So what we're going to have is basically a function which takes our state changes in and returns a list of state change view models out. So we'll create our list of view models, and then what we're going to do is we're just going to loop through those state changes and yank out from using the index the current state. Now, we need to determine what the end date is for this particular state. So what we're going to do is we're going to index forward 1 in the array to get the next state start date to be the end date. Of course, we need to be careful we don't index off the end of the array. So we have an if statement to protect us from that. So, and then if we are in the final position in the array, we obviously grab the now time to use as our end date. We use our object initializer to create our view model and calculate our duration by subtracting the start date away from the end date. Then we take that view models and then add it to the view models list, and eventually, once we've gone around that loop, we return the view models. Now that's pretty typical code. It's not particularly difficult, but we could improve it a lot by, again, lifting our level of abstraction up and thinking about sequences and thinking about how we could write this in a declarative style rather than this imperative style. So let's take a step back and think about the problem. So what we've basically got here is effectively 2 sequences of dates. We've basically got our start dates in a sequence, and we've got our end dates in a sequence. And what we basically want to do is subtract those 2 off of each other. So we want to be able to walk through those 2 sequences together and then subtract off each pair. So naturally, that being an operation over sequences, we can hope that there's something in our DSL for sequences, which in this case is LINQ, to help us do that. And there's a function called zip. So what we're going to do first is get our two sequences. So we've basically got our sequences of start dates already. That's our state changes list. That's basically the same thing. And what we now need to get is our sequence of end dates here. We can do that here by basically just taking our state changes, skipping the first one so that we end up starting on state 2, and then concatenating to the end of that sequence an additional state change which contains our now time, right? So that means we now have both this sequence and this sequence here. So then what we want to do is basically step through those two sequences together. So we're going to use zip to do that. So zip takes two sequences, the state change and then the next states, and then you give it a lambda where it basically calls the lambda with each pair. So we'll take our current and our next states, and then we'll use an object initializer to calculate our duration by doing the subtraction, and then to list that out and return it. So you can see when we transform this into using a declarative style and used a LINQ as our DSL over sequences, we're able to write code that's a lot more simple and a lot more readable, and it's also a lot shorter. So this is sort of the perfect example of a case where we could write how to get what we want, and this, our imperative version here is literally saying how to get what we want. We want to index forward in an array and look forward, but we don't want to go off the end. So we're managing all these little bits ourselves, managing that state. Let's not manage state. Let's lift ourselves up and declare what we want rather than how to get what we want. Okay, so so far we've sort of looked at DSLs over sequences. Another thing we work a lot with in languages like C# and JavaScript is nullable types. So we can make our lives a little bit easier by programming functionally when we're dealing with nullable types. So here's a very typical example of a bunch of null checking you've probably written before. So again, we've got some application, and on it we have, say, some identity details of someone filling their stuff out. And on that, we have their address. And then on their address, we have their suburb. And here, we basically want to pull out that suburb. But of course, the path could be null along the way at any point, right? So we need to make sure that it's not null so we don't get our null reference exception. And if it is null anywhere along the way, we basically want to return unknown as the suburb. So we start with that. We do an if statement. And then if we can get to where we want, we side effect against suburb and overwrite it with the value that we want. So this is using statements. Let's see if there's a way to write it using expressions instead. So the first thing we want to do is add a couple of tools to our toolbox. So we basically want to write this little maybe function. And what this maybe function does is it's an extension method that extends off of, in this case, reference type. So T can be any reference type. That's what this is saying here. And then it takes a function which takes whatever that T is and returns something. So that can be whatever that lambda decides it wants to return. So the implementation is very simple. All we do is we use a ternary expression to say, is our T, our object, not null? If it isn't null, call the function with it. If it is null, return whatever the default value of T return would have been. So if T return was like a string, so some reference type, then it will be null. If it's a value type, it'll be the default of whatever that value type is. Similarly, we have a version for value types, nullable value types here as well. So this particular version takes a T, which is a value type, so a struct, but it's a nullable value type. So it has uses has value and then does a very similar thing. So if we use this maybe function, we can write to that null checking instead using expressions rather than our statements. So here what we can basically do is say, grab our identity details. Maybe if it's not null, access the address. Maybe if the address is not null, access the suburb. And then what we're going to do is we're going to use the null coalesce operator to basically fall back to the unknown value if anything along this path is null. Because if this is null, then this will not run and this will not run, right? Well, the lambda won't be called. You'll just fall back to null. If address is null, then this lambda won't be called because the address was null. So it just flows and composes through quite nicely. That's such a nice pattern that in C#6 they actually decided to lift that idea up into the language. So that's a great example of more and more sort of functional ideas getting incorporated into the language. So in C#6 you can actually get rid of the maybes altogether and just use your conditional member access operator. So in here you can basically, you just go question mark dot and you sort of get the same behavior where identity details if identity details is null, we won't access address, and if it isn't, we'll access it, and so on. So that's a much terser way of writing the same logic. However, that doesn't mean that the maybe method can just go in the bin. It's still got its uses. So imagine the case here where we basically want to drill into the same data structure, but instead of grabbing the suburb, we want to grab whether or not it's an apartment address, and then we want to say yes or no is the string, because think maybe we're displaying this in the UI, and we just don't want to display true or false. We want to give it a bit more of a friendly human, we're going to use friendly human words. So here again, we're using if statements. We're side effecting into is apartment, yes, no. Let's tighten this up using that conditional member access operator and maybe. So we can basically do identity details question mark dot address, so optionally access address, and then maybe if address is not null, look at the apartment and use a conditional to a conditional expression to transform yes or no. So maybe is great when you want to drill through a path, but you maybe also want to do a transform and run a bit of code at the same time. The conditional member access operator is great, but you can't do that. You can't do this with that. So this should still be in your toolbox to allow you to keep writing those declarative expressions rather than writing statements. So we've sort of seen a few examples in C# now. Let's switch over and have a look at a few examples in JavaScript instead. So I've got VS Code here. I can't make that any smaller. So what I've done here is I've made a few examples in Node. They're quite simple. And this first one is basically porting the logic we did for splitting full names into JavaScript. So you can kind of see here that the things that you learn and these libraries that you learn in C#, that's not wasted knowledge. That sort of DSL over sequences is widely reusable across languages. It might look a little bit different, but the ideas and those concepts are the same. So if you go looking in JavaScript, you can find a library called lodash, which will give you that DSL over sequences. If you go to F#, you've got the same sort of thing there. If you go to Scala, you've got the same sort of thing there. If you go to Haskell, again, it's the same sort of thing. So these ideas and these knowledge, you don't lose it when you move from one platform to another. So JavaScript tends to come with a pretty anemic standard library. You don't get much out of the box, but that's where the open source community has sort of stepped up, and there are lots of libraries that you can pull in to fill in the gaps. So if we want this DSL over sequences of values, this is where a library called lodash can come in and save the day. So lodash is sort of the successor to a library called underscore, which was called underscore because it used the underscore, and then lodash, I think they played on the name, and that's how they sort of got the lodash name. So in this particular example, what we're going to do is, again, do this full name splitting. So we're going to split by string, and in this case, we don't have that overload to just eliminate empty strings for us, so we'll just do a filter ourselves by hand to get rid of the empty strings. Then we'll create an object with those properties. And you'll notice that, again, we're using underscore dot, and we've got those very similar functions that we had in LINQ. We've still got them in JavaScript. So in this case, we can call first on our array of names, and it will return the first. And I think it returns undefined if that is empty. So that's why we use basically a truthy check to fall back to null, because I'd rather have null than undefined here. For surname, we've got ternary expressions in JavaScript, so we can do the same sort of thing here. We've got a last, so we can call that. Now for middle name, it's a little bit different. So JavaScript and C# aren't the same, obviously. So in C# to compose functions nicely, we tend to use extension methods. In JavaScript, there are a number of ways of achieving the same sort of thing. So in this version of lodash, there's a function called chain, which they've basically implemented, which what we'll do is you give it the input to your chain of function calls, and it returns some object which you could continually dot off of and build up that set of operations. So in this case, we start out with chain. We do a drop to skip our first one. So notice it's drop rather than skip, but it does the same sort of thing. Take, we do a join, and then value is how we sort of exit out of that chain and get our final value out of it. So if I run this, I can prove that it does work. So it runs. And splits up our names as we expect. So you can kind of see here that we're also able to lift our level of abstraction up and write declarative code in JavaScript as well. Now, the Lodash team this is the sort of code that you might write if you're using a slightly older version of Lodash. If you're coming in new, you'll probably use the latest version, in which case they've got a slightly different way of composing functions, because what they realized is when they implemented chain is that the way chain is implemented requires them to basically pull in all of Lodash require the whole thing in. Now, when we're bundling up our JavaScript and sending it to the client, we want to try and keep our bundle as small as possible, so we're not using up too much bandwidth and we don't want it to be slow. So Lodash is kind of a kitchen sink of lots of different functions. So if you only use a small subset of them, why send all across all the ones you're not using? So they didn't really want you to have to require in all of Lodash. They just wanted you to be able to require in the bits that you wanted. And Chain didn't let them do that, not in a clean and easy way. So in Lodash 4, they implemented an FP sort of module where you can individually require in functions you want. You don't have to, but if you're trying to keep your bundle size down, then this does help. So you can see here I've required in all the same functions we were using before, but this time the way we compose them together, we don't use chain, we use flow instead. Now flow is a function which basically takes multiple parameters. So JavaScript being dynamic, we can pass as many parameters to a function as we want and it can figure it out later. So you basically just pass as many different functions to flow as you want. And then flow returns itself a function which you call with the input to your chain of functions. So again, here we're just calling drop, take, and join. But it's a bit weird this time because we're not dotting things together. We're sort of calling drop and then it returns something which goes into flow and somehow magic happens. So let's see how that magic works. So what the Lodash guys have done is they've basically picked up a technique from functional programming land called function currying. So here's an example of an uncurried function, and these are what we're typically used to writing in C# and JavaScript. Basically functions that have more than one parameter, right? So here's an example of how you'd write drop in that uncurried form. So you'd have count and array as two distinct parameters on the function. If we were to curry this function, we need to be able to reduce it down so the function only ever takes one parameter at a time. So my drop down here is the curried version of that. So it takes one parameter, the first one, count, and then returns a function that takes the next parameter, array, which when invoked does your action. So that's kind of how they split up those multiple parameters into functions that each take one parameter at a time. So down here you can kind of see how that's invoked. So you call myDrop with the first parameter, it returns a function, you invoke that, and things happen. So that's what's happening up in here when we compose together our functions. So we're calling drop one here, and what that's doing is returning a function that when given an array will drop one thing from that array and return an array. And then take was returning a function that when you give it an array, it will return an array. So what flow is basically doing is very simple. It returns a function that when you give it an array, it will pass that array to the first function here. That function will take it, return something. Flow will take the return value from the first function and pass it as the input to the second. The second function will do something, return something. Flow will take the output from that, pass it as the input to this, and so on and so forth. So you can basically flow together many functions into a single larger function. So this is basically how functional programming languages do functional composition. They compose together these functions into a wider function, and that's exactly what flow is doing. So flow here, all of that expression is returning a function that is the composition of those inner functions. So another interesting thing about the way this is done is you can introduce your own functions here. So if there isn't one in that bag, and there probably is because Lodash has a ton of them, so always look in their doc to see whether there's something that does what you need before writing your own. But if you want to, you can actually put your own functions in here, and they can just participate because this thing just composes together any old functions. So if I put in the one I implemented below and run this, it'll work just fine, even though it's not a function that was from Lodash. So if I switch over to this example, this is another good example of where if we were to write this code in an imperative style, we'd end up having to write a bunch of state management code. when really we just want to state what we want and get it. So this particular example, we've got a list of users, they have email addresses and names, and what we want to do is write a bit of logic that figures out whether or not an email address appears more than once in this list of users. So maybe we can put a warning up in the UI and say, hey, you've entered the same thing in twice. So in this particular example, what we're going to do is we've pulled in all of lodash FP. So I can't be bothered pulling in each of the functions by hand here, so I can still do the same underscore dot and get my functions. So we're flowing together a number of different functions here. The first one being count by, and what that's going to do is it's going to take our list of users, and then it's going to run a lambda for each of the users, and the lambda is going to return some value which count by is going to count the number of times that value turns up. So in this case, what we're doing is we're returning an email address, which we're lowercasing and trimming so that if there's different casing, we ignore it, or if there's trailing spaces, we fix that up. And it will count the number of times that email address shows up. And what it will do is, in a very JavaScript fashion, it will return an object. So it won't return an array, it will return an object where the properties on the object, the property names are the email addresses, and the property values are the counts, the number of times that email address has turned up. So then what pickby will do is pickby will take an object and it will filter the properties on that object. So it will call this lambda with the name of the property, which in this case is the email address, and the value of the property, which in this case is the count, and allow us to basically filter off properties we're not interested in. So in this case, we're saying, okay, only keep the properties only keep the email addresses where the count is greater than 1, because we want to look for the duplicates or the triplicates or whatever, right? Then we can flow the output of that, which will be the object with only the duplicate email address properties on it, into keys. And what keys will do is only keep the property names and return them in an array. So effectively, we're passing in an array of users, and we're getting back an array of email addresses. So I can run it. And we get back our duplicate email address from our list. So if you think about how you'd implement that imperatively, it'd be a lot more gross than that. So you'd basically have to do something where maybe you'd loop through your list of users, and you'd take each email address and you'd put it in an array, and then as you did that, you'd say, well, is this thing already in the array? If it is, then put it in another array so that we can return that because it will contain the duplicate. So there's a lot of this basically passing around and state management that when we work at this high level of abstraction, we work with these DSLs over sequences, we don't have to do that. Instead of writing how to get what we want to declare what we want up front. So we want to use that declarative programming style. What's interesting here is that we can actually shrink this code down into an even shorter form. So what we can do here is we can actually eliminate this function altogether, because all this function is actually doing is just taking users and passing it to whatever flow returns. So that's a bit redundant. If we want to, we can actually shrink this down even further. So if we get rid of the function body and put our equals there, get rid of our return, and all we're doing here is we're just keeping the function that flow returns, and that is exactly the same code as what we had before. So when I run it, same output. So we can shrink that down even further, which is nice. All right, so what we've looked at so far is DSL over sequences of values, and sort of some DSL function over dealing with nullable types. So now let's shift gears and look at a different type of DSL that can help us. So if I switch over to a different folder, let's go over to RxJS. What we're going to look at is a use of a library called Rx, which you may or may not have heard of. Rx is pretty cool. So what we've looked at when we've looked at a sequence over values is we've looked at something where the sequences are pool-based. So when you iterate over, like for example an array, and think about a for each loop, you're basically saying, give me the next item, give me the next item, give me the next item, and then maybe you quit out early with a break or something like that. But you're in control. You get to say when I want the next value. Sequences of events are different, right? So you don't necessarily have control over the source of those events. So if you think about maybe a user moving their mouse across the screen, and as they move their mouse, events are firing with the XY positions of their mouse coordinates. You can't control how the user is moving their hand. They get to move their hand however they like. that it's just firing events, and you effectively have to catch those events and handle them as they come in. So you're not in control of the source of events. You basically receive them as they get sprayed at you. So when you're dealing with a sequence of values, you don't have to worry so much about time. You're in control. But with sequences of events, you do have to worry about time. And writing imperative code to deal with timing is hard. This is where Rx can come in handy, because not only can it deal with sequences, because it deals with sequences of events, but it can also deal with timing of events. And that's super useful, because when you can just declaratively say, deal with time for me, it makes your code so much more simple. So I've got a couple of pretty neat examples of what that could do for you. So in this particular project, it's just a little Node server, a little Node Express server that's running some stuff, and a little Angular app. So I'm not going to go into the Express and Angular stuff. It's not really the point. We'll just look at the Rx stuff. So if I switch over to the website. Okay, so the first example is a pretty typical one where we've got a user-driven search page. So here what we've basically got is a text box that they can type into, and then because we want to keep our user experience nice and live, we basically do searches as they type, as opposed to wait till they're finished and then have them press a button to execute the search. We want to keep that nice, fast user experience. So, to implement, that's not exactly hard. You just do requests as they type. But there are some subtle bugs that can come in when you just do it in a naive way. So one of the interesting things about asynchrony is that things may not necessarily come in the order that you expect. So as the user types into this box and we're sending out HTTP requests, there's no guarantee those responses will come back in the same order that we sent out the requests. Because one request may take longer than another. Maybe the network got a little bit slow. Maybe that search is a bit more expensive. Maybe your server's a bit more under load. There's no guarantee there, so you have to be able to deal with that. But when you write a naive implementation, like the code that's backing this particular page, you can get yourself into some strife. So when I type into this box and I type the term slow in, that particular request on the server side, I've forced that to be quite a slow request. And then the word slow fast, that result will come back quickly. And we'll see things come back out of order. So as I type this, we can see the responses coming back. We've got our 7th, well, it's 0 indexed. And then suddenly we flip back to our 3rd response, and it's overwritten our later response. And now we're showing the wrong search results on the screen. And this is actually more common than you'd expect. I think the latest place where I saw this turn up was on the Power website. If you go there and type into their package search, they have this issue where sometimes if things come back out of order, you get stuff coming back and overriding your search results, which is a bit annoying. Now, let's have a look at the code that implements this. So this is a bit of Angular code. If you're not familiar with Angular, don't worry too much about it. It's pretty typical. Basically, the scope is a view model on which you put things, and then the view can bind to the stuff on the scope, and you can also put functions on the scope that the view can basically call when things happen. So in this case, what we're doing is we're setting a search function on the scope, and that search function will be invoked every time the user types into that text box. So effectively, for every key press, this search function is going to get called. This search function, what it will do is immediately bundle up their search terms, and then call, do an HTTP request to our server side, pass those parameters through, and then this particular function will return a promise, which allows us to hook a callback in to receive the response asynchronously. So this is our callback here. We'll receive our response. We'll just grab the results and put them in the scope so that they're displayed on the screen. But the subtle bug here is a timing bug, where these responses, there's no guarantee that these callbacks will be called in the same order that we actually sent out those requests. So we need to be able to solve that timing issue. Now, we could do that by hand, by capturing an index using the closure, and then making sure the index that we see here is, make sure that it's not less than the one that we've set somewhere else, and we do all this munging and state handling. But that just makes our code more complicated, and we're stating how to get what we want, rather than just what we want. So we want to lift our level of abstraction up. And in this case, we can think about our problem in terms of sequences of events, and we've got a library on hand that does allow us to lift that level of abstraction up and write declarative code over sequences of events. So let's have a look at the good example. So this one is basically the same code, but instead rewritten to use Rx. So Rx is available across multiple platforms. It's in JavaScript, so there's RxJS, and there's also Rx on .NET, because that's kind of where it started, and I believe there's ports for Rx for the JVM and a whole bunch of other platforms going as well. So I'm also using a library called RxAngular, which just provides a little bit of glue between Angular and Rx, just to make things a little bit easier. So one of the things that glue provides is this create observable function on the scope. And what that will do is it will put a function, in this case called search, just like we had before, on our scope object. So this thing will mutate scope, which is a bit weird. And then it will return this observable sequence. So this search observable is a sequence of events. It represents a sequence of events. So just like before, that search function is put on the scope, and then we've got something in the view which basically will call that function every time someone types, which means that our search observable represents a sequence of events of the user typing, right? So as they enter keys into that text box, we're going to get events firing down this pipeline, right? So then what we're going to do is we're going to use like our functional combinator functions here. So we're going to use flatmap. Now, flatmap in LINQ is called select many, so there's not too much scary there. So what it basically does is it takes a sequence of sequences and then flattens it into a single sequence. So here, our outer sequence is our sequence of keystrokes, effectively, and our inner sequence is HTTP requests. So you can imagine HTTP requests being a sequence if you think about them in terms of the event of their response arriving. So they end up being sequences of one event, where the one event firing is the response, but they are a sequence nonetheless. And that's the way Rx allows you to do things. So you can actually, in here, what I'm doing is I'm just returning that inner sequence, which is that HTTP request, and that's a promise. And Rx is smart enough to look at a promise and go, oh, this is a promise, cool, I'll just treat that like a sequence of one event. So after this code here has evaluated, what we effectively have on hand is a sequence of responses now. But what's interesting here is we've actually used flatmap latest, and this is where Rx's ability to deal with time comes in super handy, because flatmap latest not only flattens a sequence, but it also deals with time, and it says that if any earlier inner events come back, just throw them away if later things have started. So this will just straight away solve the problem, and any requests that come back out of order, any earlier made requests whose response comes back after a later request has already gone out, those will just be discarded automatically by Rx. So this here is basically how we take our sequence of responses and then effectively handle each of those responses. So safe apply is something that RxAngular gives you so that you can hand it the scope, so that it can do all the Angular munging of apply and digest and stuff to make sure that when you update your view model, the view is rebound and so on and so forth. So here we're basically just taking our responses just like we were before, assigning them onto the scope, and we're done. So on the very last line, you do subscribe, and that's effectively what activates your pipeline and starts you listening to that sequence of events. So straight away, we can see that this is not a huge transform to the code we had before. In fact, the main structure, which is basically this stuff, right, is pretty much intact, and this bit here as well. And we've just changed how we've composed it together to use Rx instead of doing it by hand. And because Rx does allow us to work at that high level, we can get free stuff like flatmap latest. So let's have a look at how this will work now that we've got this new code. So if I type this in, we can see the right response comes back, and then if we wait a few seconds, there won't be any other requests coming back and stomping on my current results. So that's just solved our problem straight out of hand. Now, because we're sort of working in this functional declarative style, we can add new things to this quite easily in a very safe way. So you'll notice here, this is quite inefficient. For every keystroke that I did, I sent out a request. So I sent 8 requests here, but really, 1 or 2 might have sufficed. So we can solve this very easily by using Rx. Now, if you think about, just try and think in your head how you'd do that if you were doing imperative code. you'd have to write a whole bunch of state management to say, oh, how long has it been since the last time that the user put a keystroke in? Has it been long enough? And if it has, then send a request. I don't want to do that. You don't want to do that. We just want to use debounce. And debounce, we can just compose it in straight there. And what this is going to do is going to take that sequence of keystrokes and then transform it into a sequence where it will only allow events down the pipeline once the pipeline's been quiet for 200 milliseconds. So if no event has come down the pipeline for 200 milliseconds, it'll let only the last one through. So that way it basically throttles our rate of events down this thing. So if I now refresh this guy and type in here, we get 1 request rather than 8. And it was 1 line of code to change that. So those are the sorts of advantages that we get by working at that high level abstraction and leaning on these libraries to allow us to program declaratively. So I have a final example here, which is one which does a bit of polling. So here, what we've basically got is a little page which polls the server for state. So on a previous project that I worked on, we basically built an application form where the user could enter in a whole bunch of details and then eventually submit the thing, and it would go off and be processed asynchronously on the server side. So that processing may take a few seconds. So we basically dropped them onto a status page where we live showed them the status of their application as it moved through certain states. So you can probably see where the source of that state change example came from. So we knew that it would probably only take a few seconds for the full process to complete, so we wanted to keep that UI pretty live, so we just polled pretty quickly. But we knew that sometimes third-party services got slow, and when they did, there's not a lot we could do about it, you just had to wait. So we didn't want to just pound the server every second while this thing sat there for maybe a couple of minutes, because that's just wasteful. So what we wanted to do is basically slow our polling down so that we, eventually we were only polling every 10 seconds. So we kind of set up a little polling function which basically allowed us to poll every 1 second 10 times when the page first loaded, then every 4 seconds 10 times, and then every 10 seconds until eventually we got into the state we wanted, in which case we didn't want to poll anymore because we'd moved into, in this case I simplified it down to just loading and complete. So once we're in that complete state, we don't want to poll anymore because we're done, we don't need to. So we want to stop polling at a certain point. So we sort of polled fast, slowed down, and then slowed down further. So if we go to the code, what we've got here is how we'd construct that. So the nice thing about working with sequences of events is that we can actually write this declarative code. So if you think about polling, that is just a sequence of events. It's a sequence of clock ticks, right? So we can model that. So what we can do here is use Rx. So in this first line, Rx observable return is going to create a sequence that fires 1 event because what we want to do is basically fire immediately. So we want to poll once a second 10 times, but first we want to send one immediately. We don't want to wait 1 second. So this gives us a sequence which fires once immediately. And the value that gets fired down this sequence is null because I don't actually care what the events are in this case. All I want is the timing of them to drive something. So then to that sequence, we simply concatenate another sequence. In this case, we're going to concatenate a sequence where it ticks every 1 second, so that's interval 1,000. And then that's just a sequence, so we can say take 10, and that just limits it to no, you complete after 10. Then we concatenate to that a sequence of ticking every 4 seconds 10 times, and then to that a sequence of ticking every 10 times into infinity because we haven't limited that with a take. So that will just continue ticking every 10 seconds until eventually we want it to stop. So that gives us our polling observable, which is our sequence of events that will tick in that behavior. So we'll take that polling observable, and just like in the previous example, what we're going to do is we're going to use flat map latest to basically hook onto that and do our HTTP requests. So again, flat map latest to make sure that our responses, if they do come back out of order, just it's taken care for us. Then what we do is we take our safe apply, and as the responses come in, we apply those changes to the scope so that we can see them in the UI. So we take the state and put it in there. And now, interestingly, what we do here is we look for the completed state. And if we have completed, what we do is we take the subscription that comes out of doing a subscribe. So when you do a subscribe, back from that you get a subscription. And if you want to stop listening, what you do is you take that subscription and you dispose it. And that basically stops listening. So in this case, once we've hit completed, we don't want to listen anymore. So we just dispose our subscription and we stop ticking and we stop doing our HTTP requests and polling the server. So let's have a look at how that works in action. So let's refresh this. You can see that this is ticking up once per second, and then after 10 seconds it will slow down and start doing it once every 4 seconds. And then over on this other tab, I've basically got, I see it's gone to the 4-second stage now. Over on the other tab, I've basically got something that lets me set the completed on the server side. So let's set that completed, come back here. Oh, it's already picked it up. We're now completed. We're not polling anymore. These numbers won't change. So we've been able to write something that if you were to try and write that sort of timing logic by hand using imperative style code would be pretty hard. But when we're programming functionally and we're lifting our level of abstraction up and writing declarative code instead, and we use the right libraries, things like Rx, we can write this sort of complex timing logic in a really simple, clear way that's very understandable for other people to read and therefore quite maintainable. Okay, so that's the last coding example, so we'll just flick back to the slides and wrap up. So what we've seen today is how we can apply functional techniques to solve day-to-day problems. Functional programming features are present in our modern imperative languages, and new versions of these languages tend to bring more functional features. So we sort of saw how that C# added that conditional member access, and obviously way back when it added Lambda functions. And JavaScript itself has actually added arrow functions relatively recently. So arrow functions is their name for Lambda functions. You might have seen one of those in the examples. I put one in there. So we can see that these languages are pulling in these functional features over time. So that should give us a bit of an indication of the way things are heading. Functional techniques do allow us to program at that higher level of abstraction. We program declaratively and we state what we want rather than how to get what we want. We eliminate side effects from our code because we program with expressions rather than statements. This makes our code shorter, more readable, and therefore more maintainable. The code does look a bit different, but it's not impossibly different. It doesn't take long before you find that style of code natural to read. It's a similar step forward that the unstructured programmer took when he abandoned the goto for the for loop. Obviously, there's a lot more to functional programming than what we've seen here. This is just sort of the tip of the iceberg. But this is a great way that you can get started in your current code base and reap some real benefits. So once you get your toes wet, I think you'll quickly realize that programming functionally isn't that hard after all, and you're going to want more of it. So the slides and code for this are available up on GitHub. There's a link there, so feel free to go check them out and have a look at how things are done in more detail. And if you have any questions, please do ask them now, or if you want, you can talk to me after the session, or if you see me around, or Twitter, or whatever. So if you have any questions, please do pop your hand up. Yep?
How is the debugging story look like? So in particular with flow, which you have a series of functions, so function, function. Can you, something doesn't work, and you, I don't know, you want to know how does your data or return value looks like after, say, the second function.
Yep. So in order to do that, what you probably end up doing is composing another function in there that just, for example, prints it out to the console. Because you can easily compose other functions in there, the simplest way to check that is probably just to put a console out in there. Or if you want, stick a lambda in there and then put a breakpoint in the lambda if you've really got to pause the execution and have a look at everything there. So you can hook into it. It is a little bit more awkward because breakpoints are kind of they're sort of designed around imperative step-by-step code. So yeah, it does make it harder. It's a bit like that in LINQ as well. So sometimes it helps. So if you need to get into the middle of like an expression like that, sometimes it helps to just split the expression into two expressions, and then that way you can put a breakpoint on the result of the first half of the expression and see what it evaluates to, and then once you've finished debugging, just put it back together. So that's often the simplest way to get a debugger into that expression and see what's going on. Anyone else? Yeah?
Is currying available in C# yet, either by natively or wrapping it with F#?
So yes, if you're using F#, you will get currying. So F sharp is that's part of it, the way it does functions. It will curry things automatically for you. And it's got the optimizations to make that fast under the .NET runtime. C sharp, I don't think so. You could do it yourself, but to be honest, I don't think the code would be pretty ugly to do it. Like, you could do it, but I don't know whether on the whole that would actually make your code more readable or less readable. So it's sort of a double-edged sword there. I think if you're gonna really embrace that sort of thing, I highly recommend you look at F sharp, because it is a .NET language, so you can still get all the nice things that you've got in .NET and stay there, but you then do get a fully functional language which can do these things for you, so you get currying for free, and it just deals with it, which is cool. Yep.
Performance. Like, if you're working with a large set of data,
Mm-hmm.
how does performance compare to, like, say, style programming?
If you're doing like really, really highly performant stuff, you'll probably find it a bit slower, because yeah, you are incurring additional function calls there, and there is a little bit more like bookkeeping going on. I know I remember reading about the ReSharper guys, and they were using LINQ all over the place in their code base, and of course ReSharper needs to be really fast, like really fast. So they actually had to go and unroll a few things and do it by hand because it was a bit slower. So yeah, in those cases, if I were you, what I would do is what they did, which is basically implement it with LINQ and a nice way first, and then if you find that it is causing performance problems down the line, then unroll it and write it imperatively. But I think it's unwise to try and prematurely optimize by just going, oh, I'm not going to touch that, because in most cases, that's not where the bottleneck in your code is going to lie. In most cases, it's going to be somewhere else, like a database query or something else. It's not normally that bit of the code. But look, if you are writing code that the bottleneck does lie there, then yeah, it's going to be a little bit slower. But this is where other languages, like things like Haskell, where it's built for that, can optimize for that, and it's a bit faster in those languages. So you know, sort of you pay a cost for your readability in something like C# and F#. So anybody else? No? Okay, cool. Thanks, guys. Thank you for coming.